All right, so you've probably heard of the Monty Hall problem. And yeah, you might even know the big secret. You're supposed to switch doors. But just knowing the what isn't the point today. This is a high cognitive explainer. We're going to go way beyond the simple answer and actually dissect the formal mathematics behind this famous paradox. Think of it as a deep dive for anyone who really wants to get their hands dirty with conditional probability.
So here's how we're going to break it all down. First, we'll take that higher-level look at the paradox itself. Then we'll build up our intuition, exploring the real power of information. After that, we get to the main event, a formal proof using Bayes' theorem. Then, just to make sure we've got it, we'll see what happens when the rules change. And finally, we'll talk about the real-world takeaway from all of this.
Okay, let's get right into it. The Monty Hall problem, at its core, is this famous, almost magical puzzle in conditional probability. The whole thing really hinges on how brand new information can totally change a decision, often in ways that just feel, well, completely wrong.
So here's the classic setup. You know the one. You're on a game show, you've got 3 doors. Behind one, there's a shiny new car. Behind the other 2, goats. You pick a door, then the host, and this part is absolutely crucial. The host, who knows exactly what's behind every single door, opens one of the other doors and shows you a goat. Then he turns to you and asks, do you want to stick with the original choice, or do you want to switch to that other closed door?
Now, what makes this whole thing so fascinating is just how counterintuitive the answer is. Your gut, my gut, pretty much everyone's gut screams that it's a 50-50 shot now, right? But check this out. The problem famously made fools out of a whole bunch of PhDs in mathematics. This isn't just some simple brain teaser. It's a really profound lesson in how our intuition can completely betray us when we're dealing with probability.
So before we dive headfirst into the formal proof, let's try to build a better, more solid intuition for this. See, the key to really cracking this problem isn't just memorizing the answer. It's about understanding why our first guess is so wrong. The host opening that door isn't just for dramatic effect. It's a powerful injection of new information into the system.
And to really see why, let's blow this problem up with a little thought experiment. Instead of just 3 doors, imagine there are 100 doors. 99 of them have goats, and only 1 has the car.
Okay, you make your pick. Let's say you pick door number 27. Your chance of being right is tiny, just 1 in 100. Now the host, who knows exactly where that car is, walks down the line and opens 98 of the other doors, revealing a goat behind every single one. So now you're left with your door, and just 1 other door that he intentionally left closed. He basically just filtered through all the junk for you.
And this frames the choice perfectly, doesn't it? The host's action was not random at all. He did you a massive favor by getting rid of 98 wrong answers from the giant pile of doors you didn't pick. So the question isn't about 2 doors anymore. It's about your initial 1% long shot versus a single door that has absorbed the entire 99% probability of all the others combined. You absolutely want to switch.
So that thought experiment really helps build a strong gut feeling. But this is a high cognitive deep dive, so we need proof. We are now going to formally, rigorously demonstrate the solution using the proper language of probability.
And the tool we're going to use for that is Bayes' theorem. Put simply, it's a mathematical formula that tells us exactly how to update our beliefs when we get new evidence. In our case, our hypothesis is that my first door has the car, and the evidence is that the host opened another door and showed me a goat.
Okay, let's define our terms. First up is P of H. This is the prior probability of our hypothesis. Before anything happens, what's the chance your door has the car? Well, with 3 doors, that's easy. It's 1 in 3.
Next is P of not H. This is just the probability that your hypothesis is wrong. In other words, that your door has a goat. It's simply the flip side of P of H, so it's 2 in 3. This represents the combined chance of the other 2 doors.
All right, now things get a little more interesting. This is P of E given H. This means, what's the probability of our evidence happening given our hypothesis is already true? So what's the chance the host shows a goat given you've already picked the car? Well, if you have the car, the other 2 doors have to have goats. He's guaranteed to open one and show you a goat. So the probability is 1, or 100%.
And finally, P of E given not H. What's the probability the host shows a goat given your door has a goat? Okay, think this through. If your door has a goat, then one of the other doors has the car and the other one has a goat. The rules say the host must open a door with a goat. He can't open yours and he can't reveal the car. So he has no choice but to open the other goat door. Again, he is guaranteed to do it. The probability is also 1.
Okay, let's put it all together and prove it. Bayes' formula can look a little intimidating, but it's really just a way of organizing these probabilities. It says that the probability your door is correct after you see the goat, that's P of H given E, is equal to P of E given H times P of H, all divided by the total probability of the evidence, P of E. We can calculate P of E by adding up the probabilities of the two ways it can happen, which comes out to 1 times 1/3 plus 1 times 2/3, which is just 1. So our final calculation is 1/3 divided by 1, which equals 1/3. The math is crystal clear. The probability that your first door was the right one hasn't changed at all.
So think about what that means. The host showing you a goat gave you absolutely zero new information about the door you already picked. But the world of possibilities has now shrunk to just 2 doors. Since all the probabilities have to add up to 1, and your door is stuck at 1/3, that means the other door has to soak up that remaining 2/3 of probability. You should always switch.
The real power of this mathematical proof becomes even more obvious when we tweak the rules a bit. Let's ask, what if the host is clueless? What if he doesn't know where the car is and he just opens a door at random? This is where you see how critical the rules of the game really are.
Let's just put these two scenarios side by side. In the standard game, the host's knowledge is everything. He is guaranteed to show you a goat. But in this random Monty version, he knows nothing. He just wanders over and opens one of the other 2 doors, and it just happens to have a goat. That single change flips the entire problem on its head.
So why does it change? Let's go back to that variable, P of E given not H. That was the probability he shows a goat, given you picked a goat. In the real game, it was 1. But now, if you've picked a goat, the host is choosing randomly between one door with a car and another door with a goat. There's only a 50-50 chance his random pick will actually be the goat door. That one value changing from 1 to 1/2 changes everything.
So here's a look at the outcome in the standard game we've been working through. As the math shows, without a doubt, sticking gives you that initial 1/3 chance of winning. Switching doubles your odds to 2/3. It's a no-brainer. But look what happens with random money. In that scenario, where the host's action is just a lucky guess, the odds become exactly 50-50. And this, right here, is what matches our flawed intuition, the intuition that got all those experts into trouble. It shows that the specific rules of the system completely define the probabilities.
So, why do we care so much about a weird hypothetical game show? Because the principle at the heart of it, this idea of updating your beliefs as new, non-random information comes to light, is a fundamental concept with huge real-world applications.
This is what Bayesian reasoning is all about. It's the logic that lets your spam filter get smarter every time you mark an email as junk. It's how scientists can become more and more confident in a theory as new experiments provide more data. Fundamentally, it's a formal model for how to think rationally and make better decisions as the world gives you more evidence.
And that really leaves us with one last big question to think about. The Monty Hall problem teaches us that what we don't see, like the host's hidden knowledge or the specific rules of the game, can be just as important as what we do see. So the real takeaway is this. Take a look around. How might hidden information or the unspoken rules of a system be quietly shaping the odds and probabilities you're calculating in your own life?